Yes, I will take you to a journey who will lead hopefully into the 21st century. You hear about already something about the future, so I hope I can continue with that one. So we start the journey with the metabolomics, what I did first. Sometimes you have a technique who is working very good in a field and some other fields are adapting this one. Hopefully we can do this also for E&L. This is a part of the journey, and after I will tell you what is the outcome of my comparison. Let's go forward. So metabolomic studies are quite often. They have now a dedicated workflow how to do it. Mainly they use untargeted screening now in combination with targeted screening. It's very important to use both. What we're also doing in E&L. So my study that I was doing is our sample was a cow. It's not because we're in Switzerland, it's because it was the subject of our study. We take samples from milk, blood, urine, and rumen fluid, and we have to put this somehow into an HPLC vial that we can analyze them with GC-MS and LC-MS technologies. This is a common workflow, very well established. After we have a processing of the data, which is a little bit more complicated, but as you see later, the metabolomics fields, they define some methods how we can analyze this data very simply. After you have a principal component analysis, usually who gives you wonderful pictures, because the aim of the metabolomic study is very often to see what is the difference between two groups. We have one control group and one treated group, and you want to see what is the difference between. So you have to find out which metabolites was really changed, and therefore we have the principal component analysis. Is also a very well technique. And after you get the set of markers, signals that was different between both groups, and then you start the identification of them. And after you have the identification, you go to these beautiful pictures, which is a metabolomic network. Before there was on paper, on huge tables, where you had parts of the metabolomic network. Now we have them all digitalized. Hopefully, there's, for example, the CAC, who has a huge database of all the metabolites, and they can link it with direction to a beautiful network. And this, for example, is one of the networks that we get. And you see there is some spots colored in green, which was the metabolites that we identified who was discriminating. There's other one who was in yellow, who was intermediates, who are not really the metabolite itself, but who is in a transition state to become from one metabolite to another one. You have the reaction nodes, you know what enzymes are in this reaction. And we highlighted only here the one that was linked to our target in this case. On the side, you have another picture of it. It's more or less the same study that was published, I think, in 2021. There will be another study who will be published now soon. I just get yesterday the confirmation that the reviewer are happy with the information. So you see, it's 6 years I left this field, and I'm still on the presentations. It's good. I still get invitations to interesting conferences. This is also part of it. I was never on a dairy conference, but maybe it can be interesting one day to join one. But the most important information is you have the possibility now to get from these data, from these huge data sets, information who tells you really what is the different, what happened when you treat an animal or a human or whatever you would like with a sample. You can go for bacteria. There's bacteria genomes are already discovered, small animals, larger animals, plants, whatever you want. So the question is how you go there. For example, the human metabolome database contains more than 200,000 metabolites. That's quite a lot. If you want to detect them with your methods, it's quite tricky. And let's say you have a method to only detect 1% of all these metabolites, you still have thousands of signals. And how we get out these thousands of signals, there that people were thinking, okay, what we can use. And they find an approach to do some data deconvolution and automated peak picking to analyze these kind of data sets. This is for LC-MS already something that is done since 10 years, since I started in this field. There are several platforms, software tools who can support the metabolomic community with this one. For example, the Galaxy for MetaboHub, it's an online platform who is supporting these kind of analysis. Compound Discover is a software tool from a company who produce also mass spectrometer. You have uMetaflow, you have Gene Data. A lot of these products are used in very studies to say, okay, we have a huge data set and we would like to get out the signals in this data set. And what is about GC-MS? For GC-MS, we have also these tools since 20 years. For example, there's a deconvolution software since 20 years. It was not very easy to use it. This is why not so much people use it. But we have also the peak picking algorithm. And we have also since 20 years high resolution GC-MS systems. They was a little bit expensive, but I was working 20 years ago and one of them works perfectly. You have very wonderful data. A little bit large, but you can treat them. And nowadays, slowly, all these workflows are also adapted for GC-MS. It's a little bit more complicated than LC-MS because you have to align more signals together at the same time. I will come back later to that one. And the combination of all three is becoming more and more popular now. For metabolomics, already used quite a while. So what is with leachable studies? Extractable leachable studies has more or less the same approach. You have a sample. In this kind, it's not an animal, it's a plastic device that is used. It can be filter, tubing, syringes, vials, whatever you think as a primary packaging, or this is also important, medical device. So we put them somehow into a sample, usually by extraction. It's a little bit less difficult like for an animal. We have the same instrumentation that we use for the analysis. We also after have a processing step. We skip the part of the principal component analysis because we have only a sample that is extracted and a blank from the solvent. And then we can skip directly to the identification of all the signals that we observe. So what does say the guidelines to it? You have different guidelines. One is, for example, for medical devices. It's the ISO 10993/18. You have another one for the UPS for primary packaging. And sometimes it's even very complicated to define which of the two guidelines is to apply, because some of the devices, they can be used for both. When you think about a syringe or a nasal sprayer, they have parts that are applying to the medical devices, but they're also primary packaging if you store a drug product inside. So it can be sometimes interesting to see in which of both directions you're going. And the guidelines for both are completely different. And I have to say, a little bit conservative back in the 20th century. So for example, the guideline for the ICH say that we take the peak height for identifying what is below or above our threshold. What from an analytical point of view is a little bit doubtful. I will say they also accept the peak area, which is much more better from an analytical point of view. From the guidelines, it's okay. On the other side, the USP, they doesn't specify exactly. They say, okay, the reporting threshold has to be connected somehow to the concentration. Yes, then there is a guideline now for the SSTs that you use in your screening methods, and you have to do it more or less on the evaluation of the tick or the base peak chromatogram. And then we say, okay, we are bad people. We take a device, primary packaging, a material where we know a lot of stuff will come out. We analyze it like the guideline wanted as a chemical characterization of the device. And we get this beautiful chromatogram on the completely left side. It was an extraction with isopropanol, what is also wanted by the guidelines. And you see somehow there is a blue arrow going down where we have our internal standard, and the reporting threshold is tenfold below the internal standard. So I have my problems to put both ideas together. Yes. Another requirement from the USP is, for example, that we get peak separations. We have a database of only 6,000 extractables, leachables that can come from plastic products. When you think that only 1/3 might be in one of the methods, because we have 3 methods, you have 2,000 methods. When you think, okay, maybe I can assume a peak size of 6 seconds, I still need 200 minutes to do my method. I want to see a lab who's doing that one, and I want to see how much time I need to analyze a couple of samples. So this is not definitely an approach that we can go for. So the question is, maybe we can learn something from the metabolomics. So let's see what is the difference, what is the similarity between metabolomics and E&L. So I made a nice, beautiful comparison. So metabolomics, you have complex samples. Milk is very complex, it's full of fats that you don't need, and sugars. It's only disturbing for the metabolomic analysis. Blood, urine, it's also not very kind matrices, and human fluid. You even have some pieces of grass inside, so it's also difficult to analyze. With the E&L, it's exactly the same. You might use some pure solvent, but the authorities are also pushing now to use, for example, simulating solvents, or using, for example, the drug product and make the untargeted screening in the drug product. And the drug product can be very, very complex. If you have polysorbate inside, for example, amino acids, sugars, whatever the people from the formulation department get in mind to put inside of the drug product to help the delivery of the API. Polysorbate is also recommended to be screened by the BPOC protocol, so you already have it in your extractable study. And I will show later a chromatogram of polysorbate extract. You will see how much you can see on it. The techniques are exactly the same. We have untargeted screening methods for GCMS, LCMS, and targeted ones. So from the point of view sample, it's very complex. Techniques is the same. So what is the approach of evaluating the data? For the metabolomics, there's since 10 years a very well-established workflow to do it automatically to get the maximum of information outside that is needed. For the extractable and leachables, we are still looking on the base peak chromatogram and on the tick. This might be not so best. So I want to speak now about, can we use, for example, our real data that we generated with the metabolomic workflow. And this, for example, is what we did. We used data deconvolution software on it. And with the normal approach, we get 8 identified peaks out of it, if we want to be serious. With the automated data deconvolution, we get 32 out of it. And when you look, for example, at the chromatogram, you might see 8 peaks, but more or less there's a hill and with another hill on it, and it's quite complicated to identify these kind of things. But with the data deconvolution, we can do it. So the question is, I say a lot, what is data convolution? What it is? It's not something that is so well known maybe to most of the audience. So we'll explain it a little bit. It's not just a base correction, because this is one thing that is used by most of the softwares nowadays, that we just take left and right the baseline and subtract it from the middle one, and you get a result. The data deconvolution is a little more complicated, because it takes also into account what, for example, is the constitution of the peak, because it can be that a signal that we get is belonging to the peak on the left and on the peak that is on the right, in the shoulder of it, for example. And then, of course, you have to calculate which ratio of these signal is belonging to the first one and to the second one. And this is what the data convolution software is doing. We can also do a kind of manual data deconvolution, when you see, for example, there was a hill inside of another hill, what it is. So we can look, for example, what is the hill? This is the one on the Toft lab. We say, okay, it's a normal extractable known, and then we can subtract all the signals that belongs to this compound from the spectrum that we already recorded, and see what is the remaining. And the remaining in this case was identified. Before I had on the side not written 1 A, B, C, and D. It was 1, 2, 3, 4. After I saw that throw is equal to 1 minus 2, I put it 2 letters. Was thinking it's better. For each of these spectra here, you have on top the one that was recorded and down the one that was theoretical one from the database. And you see, for example, for the one down, you also get an identification. And what we did then, we wanted to compare it to see if it's really true. And we take, for example, 2 intense signal of the spectra that we know belongs to the compound that we identified. And it's the same one with the second compound. And then we make some extracted ion chromatogram to see really what is the chromatographic dispersion for both of them. And here you have, for example, all the extracted ion chromatograms, and you see some of them. This fourth one in the line belongs, for example, to another compound than the other 2 on top. And the third one, or the last one, what we did, seems completely different. So we had, for example, our 2 candidates and was seeing, okay, one of the signals, what we were thinking belongs to the second candidate, actually doesn't belong to the candidate. And it finds out after we was doing the automatically deconvolution, it belongs to another candidate. But this shows that we can do it manually, but the automated workflow is first faster, and second, it's much more accurate. This is another sample. This is the polysobase to show that it also works very well in LC-MS. The people in the first lines, maybe second lines with very good eyes, they can see a red dot between, let's say at 19 minutes. There is a small one. I promise you it's here. Maybe you can look later if you want. I can put this back and people can come in front and see, yes, there is one. So this is a peak that you definitely will never observe in a tick or in base peak chromatogram. But the automated peak tracking software had absolutely no problem to identify it and to detect it. And it was as a ratio of 1.6 nanogram per milliliter. So sometimes when you have to go quite deep in your reporting threshold, the only way is to make an automated approach. And you can see it works very well. You have a lot of signals around, very strong, and the automated software finds it without any problems. I don't need even to look for it to say, okay, I know it's here. Please look at it there. No, the software finds it by itself without any issues. So you see, it's working. It's possible. We just have to use it. And absolutely, there's absolutely no reason why we shouldn't use the approach from the metabolomics for E&L. And we get much more better ideas what is leaching out of our material, instead of getting some surprises later when we are doing the leachable study and confronted with some unknown peaks that could be found before without any issue. So therefore, I would like to thank for your patience to listen to just before lunch. I hope it was at least not too boring, and I'm ready for your questions now.